Hi, everyone. My name is Dante, and I'm presenting the double agent conference problem, which I designed for the CCPC contest this year. So first of all, I'm going to start by just giving the problem statement and explaining a bit what it's saying. So, we have this double agent conference, which consists of 3 events. We have a morning event, an afternoon event, and an evening event. So this is going to be important because a lot of the analysis is depending on the fact that there's specifically 3 events. Okay, so the idea here is that we want to know how many double agents attended at least one event. That's the main thing that we're trying to figure out. And so the way that this person Reader figures it out is by having a booth, check-in booth for each event. And the way that the double agents check in is they scan a finger, and there's this system that associates their finger with a unique ID number. And importantly, no one can leave after the event starts, so that no one checks in twice to the same event. So for each particular event, you have this list of ID numbers, and we know for sure that all of the ID numbers will correspond to different people because nobody checked in twice to the same event. So this sounds great until this Reader realized that the same double agent attending different events could scan different fingers, and so we could have different ID numbers corresponding to the same person. So this is kind of a bad news. So the idea here with the problem is that we want to know what's the minimum possible number of distinct double agents, assuming that this 2 distinct ID number thing happens as much as possible. So this is given that each pair of ID numbers from the same event corresponds to distinct double agents, and this is probably the most important line in the whole problem statement. And also that each individual ID number corresponds to the same double agent. So this is just assuming that that no 2 double agents have the same fingerprint. So if you see the same ID number more than once, that definitely corresponds to the same double agent. But 2 different ID numbers could correspond to the same double agent. So the input, it consists first of 3 integers, which gives you the number of check-ins for each of the events. And then we have the ID numbers for each check-in. And then the output is going to be this minimum possible number of distinct double agents. So in the first sample input, which is discussed a little bit here, what happens is that the first event, there's 3 check-ins. The second event, there's 2 check-ins. The third event, there's 2 check-ins. So the first one, the morning event, you have this ID 0, 1, and 2, which, by the way, right away tells us if we have 3 check-ins to the first event, there has to be at least 3 double agents in total, because each of these 3 check-ins will correspond to a different double agent. Now, the thing is, we have this ID 0 in the first event, and we have this ID 3 who shows up in the second and the third events. And the idea here is that, well, maybe 0 and 3 actually correspond to the exact same double agent. And so in that case, instead of there being 4 double agents corresponding to IDs 0, 1, 2, and 3, there's actually only 3, because ID 0 and ID 3 actually correspond to the same double agent who just scanned a different finger for different events. Then there's this other sample input, which is a bit more complicated, but we'll get to that later as well. Okay, so again, I said that each pair of ID numbers from the same event corresponds to distinct double agents. That's a really important line, so I'll put it right at the top of the slide now. Okay, so there's 3 events, morning, afternoon, and evening. Each ID number will either show up only to the morning, only to the afternoon, or only to the evening. So or they could show up to the morning and afternoon, but not evening, or morning and evening, not afternoon, afternoon, evening, not morning, or all 3, morning, afternoon, evening. So there's 7 different combinations that are possible for the ID numbers that will show up in the problem. So let's zoom in again to sample input 1 and see how that looks like with this representation. So the morning event, it had this ID 0, 1, and 2. The afternoon event had IDs 1 and 3. The evening event had IDs 2 and 3. And what we said earlier is that ID 0 and ID 3 can correspond to the same double agent because 0 and 3 have nothing in common, have no event in common. So you never see 0 and 3 in the same room. And because we're looking for the minimum number of double agents, we'll assume that that means that 0 and 3 are actually the same. So maybe I could have called this superhero conference or something like that too, because it's like you can't see Clark Kent and Superman in the same room, that kind of idea. So 0 and 3 we'll assume correspond to the same double agent. Now, one thing that you could notice here is that, well, the morning event had 3 double agents, and as I mentioned earlier, that means there has to be at least 3 distinct double agents in total. The afternoon event had 2, so there has to be at least 2. Evening event has 2, so there has to be at least 2. So maybe the solution could be that we just take the maximum of the morning, afternoon, and evening attendance. So the morning had 3 people, afternoon had 2 people, evening had 2 people. So maybe the right answer is just to look at what's the maximum out of these 3. And indeed, in this, at least in this sample case, that works out. And another way to think of it, so I've color-coded these numbers, we can think of, take the event with the biggest attendance. For this event, every single ID will give it a different color because this will make it correspond to different ID numbers. And then everyone outside of that event, well, we'll just use a color from the biggest event that we haven't, that doesn't conflict, that doesn't have an event in common with that other one. So this number 3, that's outside of the biggest event, well, we'll just assign it the same color as this 0 because they have nothing in common. So this is a possible strategy, but it turns out that it's not quite complete. And we'll take a look at this sample 2 to figure out why. So in sample 2, we have 9, 10, and 10 events for the morning, afternoon, and evening. And it turns out that the total number of distinct double agents is actually 11. So right away, that's telling us that, well, this maximum thing is a little bit too simple of a solution because this 11 is bigger than any of these 3 individually. But now let's try to dig into why is that the case? So if we look into this group here, so if I do this kind of a flower shape, these ID numbers here are the ID numbers that show up in at least 2 events. So these are we can call them like the 2 or 3 event ID numbers. Now, if we take any 2 ID numbers from this group, they must be different. Just like when we're looking at morning, afternoon, evening, each one individually had to be different, but also this purple group, every ID number has to be different. And first of all, this 3 and 7 obviously has to be different from everything, has to have a different color, which means that it corresponds to different double agent from everyone else, because 3 and 7, these were the double agents that showed up to all of the events. Or I should say, these are the IDs that showed up to all of the events. So if these IDs showed up to all of the events, they must be different, correspond to different double agents from all of the other IDs. Now, this 2 and 12, these ones showed up in both the morning and the afternoon events, which means that they will have at least one event in common with the morning and evening group because they both had the morning in common, and they'll have something in common with the afternoon and evening group because they had the afternoon in common. And you can make symmetrically the same kind of argument with these numbers here in the morning and evening group. So they will have something in common with the morning and afternoon group, which is to say they have the morning in common, and they have something in common with the afternoon and evening group, and so on. So every single one of these IDs share something in common with every single other one. And I will just briefly note that this is a property that's specific to the fact that we have 3 events in particular. If we had 4, then we wouldn't be able to to exploit this property, but because it's 3 events, we can. Okay, so what does this tell us? Well, we know from what I was saying earlier that this group in the morning, this will correspond to all different colors or all different different double agents. This afternoon group will correspond to all different colors or all different double agents. And this evening group has to also correspond to all different colors or all distinct double agents. And basically what I'm saying is that this purple group, which is starting to be a little bit hard to see, but this purple group of all the IDs that showed up at least twice must correspond all to different colors or to distinct double agents. So this suggests a new way to solve the problem, which is, okay, maybe it's the maximum of the green group, the red group, the blue group, and the purple group. So it's the maximum out of these 4 groups. And the idea now is that, okay, take the biggest out of each of these groups, put different colors for everything inside of the group, and then everything outside we'll just assign a color that was inside the group. So that's a little bit abstract, but what I'm saying is that, for example, so because purple was the biggest of the 4 groups, then we can start matching colors from inside to outside. So this 11 that's inside, we'll match it up with the same color of this 15 that's outside. This 0 inside, we can match it as the same color as this 6 outside. This 9 inside, make it the same color as 8. And notice that I'm always taking something that had 2 events in common and matching up with the same color of an ID that attended the 3rd event that these ones don't have in common, so that these have no event in common. I have this 13 left over, but we can't use this over in this red group because there is nothing left, and we can't use it for 14 and 4 because they will have because 13 attended both morning and afternoon, so we can't use this color for 14 and 4, which are the remaining outside groups, but we can use this 10 to match up with this 14, and we can use this 2 to match up with this 4. And at this point, we've matched up colors with everything from the inside of the purple group to everything from the outside of the group. Now, this is possible as long as the purple group is the biggest. So if we started adding some more ID numbers to the red group, then, for example, this 16, well, we could match this up with the 13, but the 17, well, we can't match it up with anything else because all of the all of the other colors that are outside of the red group are already matched up with something inside of the red group. But what this is really saying is that the red group is now the biggest group. So again, it's you take the biggest of these 4 color-coded groups, and the solution is actually just the size of that biggest group. So this is maybe a little bit hand-wavy, but there is a way to prove that mathematically as well. You can do it by a proof by contradiction. I won't go through it exactly, but the idea would be that assume that some particular group, say the purple group, is the biggest group, and that you cannot have all of the distinct double agents correspond to some color inside of the group, as in you would run out of colors to match up from the inside to the outside. You'll end up with a contradiction where it'll turn out that if you ran out of colors, that would actually mean the purple group is not the biggest group. So this is if that didn't make sense to you, don't worry too much. The idea is just that the solution is going to be the max of these 4 color-coded groups. So it's the max of how many were inside of the green group, how many, so just think of that circle as just how many were just inside of that green group, and then how many were inside of the red group, and then how many were inside of the blue group, which up to here is really just the same thing as what we had in the previous slide, but also how many are in this purple group. So the maximum of these 4 color-coded groups will give you the solution. And there's other ways to solve this problem. This actually isn't the way that I originally solved it. I solved it in a slightly tiny bit more complicated way that still worked, but this way to me seems a little bit easier because they're just splitting into 3 different groups. And I think it was Henry who solved everything in an hour and a half when I saw his solution. It used this kind of strategy, and actually I like this better. So I'm presenting Henry's solution instead of the one that I originally came up with. So now I'll show you how you could implement this in Python. So again, I'm just re-showing you the input and the output to refresh your memory. And I am going to take advantage of this, that we know that this maximum is 100,000. And first of all, we're going to look at the total number of participants per event. So again, that's like that was the green, the red, and the blue groups, morning, afternoon, evening. That's what these 3 numbers are. And that's just the first line of the input. So we're just grabbing that first line. And then we want to construct the purple group, which again, the purple group is all of the ones that showed up in, oh, that's not purple. The purple group, that was all of the ones that showed up to 2 or 3 events. So in order to figure out what this purple group will look like is to have a Boolean list for each event. And we'll be saying, okay, in the morning, just put a true every time someone attended the morning. In the afternoon, set a true, and we'll just have it max. So this is all the possible ID numbers. We'll just set them to true inside of the list if they attended the event. And then we're going to try to count 2 or 3, which is the size of this purple group. So we'll go through each of these lists. So first we'll go with the morning list, which is the second of the 4 lines of input. And this is just the Python way to take space separated integers and put them into a list. I mean, maybe there's a better way, I don't know, but that's the way I was using. And then for each index in the list, we'll set the this morning array of the morning group to true to tell us, okay, that person did attend the morning event. Then we'll do something similar, but a little bit more complicated for the afternoon. So we start in the same way. So up to this line, it's the same thing. We're just we're flagging which events are we're flagging for the afternoon event which IDs attended. And then for each one, if it attended in the afternoon, so if I was in this list, and if this ID I also showed up in the morning, then we're going to increment this purple group because we're going to increment how many people showed up, how many IDs showed up to at least 2 events. Then we'll do something similar for the evening. We actually don't need an evening array just because we're using these arrays to look back to see, did this person also attend an earlier event? So it just turns out we don't need to bother with an evening array. But in this case, now we're checking, well, if somebody showed up to the morning event and the evening event, then we should count in the 2 or 3. If they showed up in the afternoon and the evening, then we should count them. If they showed up in both the morning and the afternoon, then we actually already counting them in the 2 or 3 because of this earlier line. So if they showed up morning, afternoon, and evening, we don't need to double count. So this not equal to is just checking that the ID I showed up in exactly one other previous event between the morning and the afternoon. So not equal, this is, think of it as XOR, or checking, did it show up the ID show up in exactly one previous event? And if so, increment the 2 or 3 group, or the purple group. And then finally, this is the magic formula that I was discussing in the previous slide, which is just we're going to print the maximum between the morning, afternoon, evening groups, or this 2 or 3, this overlap group. And it turns out the maximum out of these 4 will give you the minimum number of distinct double agents who attended the conference. So that's the end of my presentation. If you'd like to a better explanation, if you find it unclear or something like that, I am on the Competitive Programming Club Discord. My name is Dante B in the Discord. So yeah, just let me know if if you want to know more details about this problem or any other programming contest problem that I have designed. So thank you very much and have a great evening.